Let's begin our exploration of valve circuitry by going through their internal operation, starting at the filament and working outwards. Valves work by controlling and manipulating a flow of electrons, so a logical place to start is to look at the place where these electrons come from. As you know from our first videos, the outer layer of electrons are loosely bound to their atoms in metals. This is why they can move about and carry a flow of electricity. These outer electrons are said to form the conduction band in conductors. This is essentially just a band of energy occupied by these loose electrons as shown in the diagram on the screen. Since the electrons are still bound to their atoms, they require some extra energy to escape from the surface of the metal. This energy is called the work function. The easiest way to give the electrons enough energy to overcome the work function and escape from the surface of the metal is to heat them up, although they can also be pulled out by very high electric fields. And this is why valves have a glowing filament or heater. When an object gets hot, the electrons can boil out of it if they gain enough energy to overcome the work function. In the original valves, and still in some special purpose ones, the electron supply came directly from the filament itself, and these type of valves are called directly heated. However, it was soon found that using a separate cathode heated by the filament was better. This system is called indirect heating. The advantages of having a separate cathode include that the filaments and their supplies are isolated from the signals, so that they don't leak out of the device and onto the filament power supply lines, and that the filaments can be powered by AC. There's no need for a low voltage rectifier, without too much mains interference, which is known as hum, getting onto the signal. A typical filament voltage is about 6.3 volts. The cathodes are often treated with a low work function material like thoria or thorium dioxide or a strontium barium oxide. This allows them to operate at lower temperatures and lengthens their lives. Valves without this feature are known as bright emitting valves because the filament is hotter. Over time, no matter what type of valve you use, the cathode can degrade, leading to a reduction in performance. The laws governing the emission of electrons in these circumstances were discovered by Owen Richardson and others, and are summarized by the formula on the screen, where T is the temperature, K is Boltzmann's constant, and A is a constant called the Richardson-Dushman constant. Notice that this is an exponential type curve. To make a diode, we can simply place a positively charged electrode near the cathode. This electrode is known as the anode or plate. Although the first valves had a simple linear arrangement of their electrodes, as shown in the diagram on the screen, it was soon discovered that making the components into coaxial cylinders made the device more efficient in terms of space and energy. If we were to vary the voltage on the plate, VA, in a valve with a tungsten filament, the graph we would get would look as that shown on the screen. This graph presents a couple of mysteries. Firstly, why does the current flow in region A when the anode voltage is actually negative? Well, this small tail current is the result of the highest energy electrons emitted by the cathode actually having enough energy to overcome the repulsion of the anode and be picked up. Region C is known as saturation, and the curve flattens out because all the electrons being emitted by the cathode at this temperature are now being collected by the anode. Obviously, this being the case, increasing the anode voltage won't have any effect, as the electrons are being emitted by the cathode's heat, not the anode field. Now, region B might seem a bit of a mystery. If the anode is at all positive, why isn't it collecting all the electrons emitted from the cathode? Well, what actually happens is that electrons which have already been emitted repel those which are behind them, and a cloud forms which is called the space charge. This builds up between the cathode and the anode and impedes the progress of further electrons. Equations were developed to predict the current density in this region, and an example is shown on the screen now, where D is the space between the anode and the cathode. Note that in this equation, the dimensions are in centimeters. Now, if the electrons hitting the anode have a high enough energy, they can knock other electrons out of the anode, and this phenomenon is called secondary emission, and we'll come across it again later. Having established some of the basics, let's move into our first amplifying valve, the triode.